The Hubble Ultra Deep Field is an image taken by the Hubble Space Telescope over the course of 11.3 days in 2003 and 2004. To create it, astronomers pointed Hubble at a patch of sky in the constellation Fornax, a region that appeared completely blank to the naked eye, devoid of any visible star. Not a single star bright enough to be seen without a telescope lay in that direction. They left the shutter open through hundreds of separate exposures, accumulating light from sources too faint for any previous instrument. When the image was processed and assembled, every object in it was revealed to be a galaxy, not a star, not a nebula, a galaxy. The image contains approximately 10,000 galaxies, packed into an area of sky so small you could cover it with a grain of sand held at arm's length. Some of those galaxies appear as they were more than 13 billion years ago, when the universe was only a few 100 million years old, so young that the first generations of stars were only just beginning to form. The patch of sky captured in that image represents 1/13 millionth of the entire sky, and in that 13 millionth, there were 10,000 galaxies. That image, more than almost any other single piece of data in the history of science, changed the way humanity understands its place in the cosmos. Before the Hubble Deep Field observations, we knew galaxies were common, but the visual evidence, the overwhelming sight of 10,000 galaxies where our eyes could see nothing at all, communicated the scale of the universe in a way that statistics alone cannot. The universe is filled in every direction with galaxies, each one containing hundreds of billions of stars, each one occupying a volume of space incomprehensibly larger than any human scale. Tonight, we rest in galaxies, in the great slow turning of these vast stellar cities, some of which have been rotating since shortly after the Big Bang. In the deep, patient processes of their formation and evolution, their collisions and mergers, their ancient supermassive black holes sleeping at their centers, their satellite dwarf galaxies drifting in wide, slow orbits around them, and the cosmic web that connects them all across billions of light years of space, in the extraordinary diversity of their shapes and sizes and ages and activity levels, from tiny spherical dwarf galaxies of only a few thousand stars to giant elliptical galaxies containing trillions. Every fact I am going to share with you is true. Every distance, every age, every discovery. Galaxies are among the most extraordinary structures in the observable universe, and tonight they are your bedtime story. Take a slow, deep breath in all the way. Let your lungs fill completely. Hold it just for a moment, and breathe out slowly all the way, feeling your body settle and release. Let your shoulders drop. Let your hands rest open. You are inside a galaxy right now, a very ordinary galaxy, one of about 2 trillion in the observable universe. It has been turning for about 10 billion years. It will continue turning for billions more. And it does not need anything from you tonight, only rest. A galaxy is a gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. The word comes from the Greek word for milk, referring to the Milky Way, the faint band of light visible across the night sky from a dark location. That band of light is the combined glow of hundreds of billions of stars and the disk of our own galaxy, seen from the inside, edge on, looking along the plane of the disk. Every star visible to the naked eye anywhere in the night sky belongs to the Milky Way. The other galaxies, the trillions of them that fill the universe, are so far away that only the nearest few are visible without a telescope. The Milky Way is a barred spiral galaxy. Seen from above, it would appear as a bright central bulge surrounded by a flattened disk of spiral arms, the whole structure wrapped in a large, roughly spherical halo of older stars and globular clusters. At the center of the bulge is a bar of stars, and the spiral arms emerge from the ends of this bar. Our solar system lies about 26,000 light-years from the galactic center, roughly halfway out in one of the spiral arms called the Orion Arm, or the Local Arm, a relatively minor spur between two of the major spiral arms. The disk of the Milky Way is about 100,000 light-years in diameter. The central bulge is about 10,000 light-years thick. The disk itself is about 1,000 light-years thick in the region of our solar system. The halo of stars and dark matter extends much farther, perhaps 200 to 300,000 light-years from the center. The Milky Way is estimated to contain between 100 and 400 billion stars, though the exact number is uncertain because most of the disk is obscured from our view by clouds of interstellar dust that block visible light. The Milky Way contains more than just stars. Between the stars is the interstellar medium, a diffuse mixture of gas, mostly hydrogen and helium, with trace amounts of heavier elements, and dust, tiny grains of silicate and carbonaceous material, typically about a micrometer in size. The interstellar medium is far from empty. In the densest regions, called molecular clouds, the gas is cold and dense enough for hydrogen to exist in molecular form rather than atomic form, and for complex organic molecules to form and survive. These molecular clouds, some of them hundreds of light years across, are the sites where new stars are born. Star formation is ongoing in the Milky Way today, with new stars being created in the spiral arms where the density of gas is highest. Let your breathing settle gently. The Milky Way is turning around you at this moment. The Sun is orbiting the galactic center at about 230 kilometers per second, taking about 225 million years to complete one full circuit. The last time the Sun was in its current position in its orbit, the dinosaurs had only recently appeared on Earth. Before that orbit, it was the middle of the Permian period. Each galactic year, 225 million Earth years, is a unit of cosmic time that dwarfs all of human history. Galaxies come in a remarkable variety of shapes and sizes. The classification system most commonly used was developed by Edwin Hubble in the 1920s and is called the Hubble sequence, or the tuning fork diagram, because of its shape when drawn out. At one end are elliptical galaxies, ranging from nearly spherical to elongated, smooth in appearance, containing mostly old stars and very little cold gas or ongoing star formation. They are designated with the letter E and a number from 0 for nearly circular to 7 for highly elongated. At the other end of the tuning fork are spiral galaxies, divided into two branches, depending on whether they have a central bar of stars or not. Ordinary spirals are designated S, followed by a letter from A to C, indicating how tightly wound the spiral arms are and how dominant the central bulge is. Barred spirals are designated SB by the same convention. Connecting ellipticals and spirals on the tuning fork are lenticular galaxies, designated S0, which have the disk structure of spirals, but the older stellar populations and lack of spiral arms characteristic of ellipticals. Beyond these main categories are irregular galaxies, those which do not fit neatly into the elliptical or spiral categories. Irregular galaxies often have chaotic structures with patches of intense star formation scattered apparently randomly. Many irregulars are the result of gravitational interactions with neighboring galaxies, their original structure distorted and disrupted by tidal forces during a close encounter or merger. The Magellanic Clouds, the two nearest satellite galaxies of the Milky Way, are irregular galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud are two dwarf galaxies that orbit the Milky Way at distances of about 160,000 and 200,000 light-years respectively. They are visible to the naked eye from the southern hemisphere as detached patches of the Milky Way, prominent enough to be familiar to navigators in the southern hemisphere for thousands of years. Ferdinand Magellan's crew observed them during the first circumnavigation of the Earth in the early 16th century, and they were named after him in European cartography, though of course they had been known to southern hemisphere peoples long before. The Magellanic Clouds are actively forming stars at a high rate, particularly the Large Magellanic Cloud. One of the most dramatic events in recent astronomical history was the explosion of a supernova, SN 1987A, in the Large Magellanic Cloud in February 1987. It was the brightest supernova visible from Earth since Kepler's supernova in 1604, reaching naked-eye visibility for months. A burst of neutrinos from the core collapse that triggered the explosion was detected by neutrino detectors in Japan, the United States, and the Soviet Union, arriving at Earth about 3 hours before the light of the explosion, because the neutrinos escaped from the stellar core immediately, while the light had to fight its way through the collapsing stellar envelope. SN 1987A remains one of the best-studied supernova ever observed, and the expanding ring of material ejected by the explosion continues to be monitored by telescopes to this day, providing a real-time laboratory for the study of stellar death and the production of heavy elements. The Andromeda Galaxy, formerly designated M31 in the Messier catalog, is the nearest large spiral galaxy to the Milky Way and the most distant object visible to the naked eye under good conditions. It lies about 2.5 million light-years away, so the light you see when you look at it left the Andromeda Galaxy when our ancestors were early members of the genus Homo, before modern humans had evolved. Andromeda is larger than the Milky Way, with an estimated diameter of about 220,000 light-years and possibly twice as many stars, though estimates vary widely. Andromeda is approaching the Milky Way. Gravitational measurements show that the two galaxies are moving toward each other at about 110 kilometers per second, and in about 5 billion years they will collide and begin the process of merging. This merger will be one of the most dramatic events in the future of our galaxy, a slow-motion collision lasting hundreds of millions of years. During the merger, the tidal forces will distort both galaxies, pulling out long streams of stars called tidal tails, disrupting the spiral arm structures, and triggering massive waves of star formation as gas clouds collide and are compressed. The two galactic centers, each harboring a supermassive black hole, will eventually merge into a single, larger black hole at the center of the combined galaxy. The result will likely be an elliptical galaxy, or a large elliptical, very different in appearance from the two spirals that went into it. The Milky Way and Andromeda are the two largest members of the local group, a collection of about 60 galaxies bound together by gravity in a region about 10 million light-years across. The local group is dominated by these two spirals and their satellite systems. The Milky Way has at least 61 known satellite galaxies, small dwarf galaxies orbiting in wide paths around it. The Sagittarius dwarf galaxy is currently being absorbed by the Milky Way, its stars spread into streams that wrap multiple times around the galaxy. Andromeda has its own collection of satellites, including M32 and M110, two dwarf elliptical galaxies visible in long exposure photographs as companions to Andromeda's disk. Beyond the local group, at a distance of about 65 million light-years, lies the Virgo cluster, the nearest large cluster of galaxies to our local group. The Virgo cluster contains more than 1,300 galaxies, ranging from large spirals and ellipticals to hundreds of dwarf galaxies. The cluster's mass is dominated by its dark matter halo and by the hot intergalactic gas that fills the space between its galaxies, glowing in X-rays and detectable by X-ray space telescopes. At the center of the Virgo cluster is M87, one of the most massive and famous galaxies in the observable universe. M87 is a giant elliptical galaxy containing an estimated 2.4 trillion stars, about 6 times the stellar mass of the Milky Way. At its center is a supermassive black hole with a mass of about 6.5 billion solar masses. In April 2019, the Event Horizon Telescope collaboration published the first direct image of a black hole's event horizon, and the subject of that image was the black hole at the center of M87. The image showed a bright ring of superheated gas surrounding a dark central region, the black hole's shadow, exactly as predicted by general relativity. The black hole's event horizon is so large that it spans a distance greater than the entire solar system out to Neptune, and it is surrounded by a jet of material, an active galactic jet, that stretches for thousands of light-years from the center of M87 in a narrow bright beam of plasma, moving at close to the speed of light. This jet is powered by the black hole's activity. When material falls toward the black hole, it forms an accretion disk, a swirling, superheated structure of infalling gas. Some of this material is captured by the black hole's magnetic field and accelerated outward in a narrow beam perpendicular to the disk, forming the jet. The jet of M87 was first observed in 1918 by the astronomer Heber Curtis, who described it as a curious straight ray. It is one of the most well-studied relativistic jets in the universe. The Milky Way also has a supermassive black hole at its center, called Sagittarius A star, with a mass of about 4 million solar masses, much less massive than M87's black hole. Sagittarius A star is currently relatively quiet, in what astronomers call a low luminosity state. It accretes very little material compared to the actively feeding black holes and more luminous galactic nuclei. But it was not always so quiescent. There is evidence that Sagittarius A star was far more active in the past, perhaps millions of years ago, and that it produced enormous outflows of gas that created bubble-like structures extending tens of thousands of light years above and below the galactic plane, detected by the Fermi Gamma Ray Space Telescope and called the Fermi bubbles. Let your breath slow and deepen. The Milky Way's black hole is sleeping 26,000 light years away in the direction of the constellation Sagittarius. The stars at the center of the galaxy orbit around it, some of them at speeds of thousands of kilometers per second at their closest approach. The whole galactic center is a region of extraordinary activity and density compared to the quiet suburb of the galaxy where our solar system lives. The Laniakea supercluster is the name given to the large-scale supercluster of galaxies that includes our local group, the Virgo cluster, and many other galaxy groups and clusters. The name means immeasurable heaven in Hawaiian, chosen to honor the tradition of Polynesian navigation by the stars. Laniakea is about 520 million light-years across and contains the mass of about 100 million billion suns, distributed among approximately 100,000 galaxies. Our local group sits near the outskirts of Laniakea, far from the concentration of mass at its center. The center of the Laniakea supercluster is a region of concentrated mass that astronomers call the Great Attractor, a gravitational anomaly that our entire supercluster, along with neighboring structures, is slowly flowing toward. The Great Attractor has been known since the 1970s and 1980s, when measurements of galaxy velocities revealed that our local group is moving at about 600 kilometers per second toward a region in the direction of the constellation Centaurus. The Great Attractor itself is thought to be a concentration of galaxy clusters, including the Norma cluster, and possibly much of the mass of the Laniakea supercluster converging at its gravitational focal point. The Messier Catalog is a collection of 110 astronomical objects compiled by the French astronomer Charles Messier in the 18th century. Messier was a comet hunter, and he compiled his catalog to avoid confusing the nebulous, comet-like objects he kept encountering with actual comets. His catalog, published in stages between 1771 and 1784, contains many of the most famous and visually striking galaxies, nebulae, and star clusters in the sky. Among the galaxies in the Messier catalog are M31, the Andromeda Galaxy M33, the Triangulum Galaxy M51, the Whirlpool Galaxy M81 and M82, a pair of interacting galaxies in Ursa Major, M87, the Giant Elliptical in Virgo, and M101, the Pinwheel Galaxy. These objects are among the most studied and most photographed galaxies in the sky, familiar from countless telescope images and the cover of countless astronomy textbooks. The Whirlpool Galaxy M51 is a grand design spiral galaxy about 23 million light-years away, interacting with a smaller companion galaxy, NGC 5195. The two galaxies are connected by a stream of material, and the gravitational interaction between them has enhanced the spiral structure of M51, producing the beautifully symmetric arms that give it its common name. This pair was the first spiral structure ever identified in a galaxy by Lord Rosse using a large reflecting telescope in 1845. Images of M51 from the Hubble Space Telescope and the James Webb Space Telescope show the spiral arms in extraordinary detail, with dark lanes of dust, bright star-forming regions, and the gravitational interaction with its companion all clearly visible. Centaurus A, formerly NGC 5128, is one of the nearest and most studied radio galaxies and active galactic nuclei. It lies about 13 million light-years from Earth. In visible light, it appears as a large elliptical galaxy with a prominent dark dust lane cutting across its center, the remnant of a smaller spiral galaxy that was absorbed by the giant elliptical. At the center of the dust lane, a supermassive black hole with a mass of about 55 million solar masses is actively accreting material, producing two enormous jets of plasma that extend about 25,000 light-years from the center in opposite directions perpendicular to the dust lane. These jets emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, making Centaurus A one of the brightest radio sources in the sky and the brightest active galactic nucleus visible from Earth. Quasars are the most luminous class of active galactic nuclei, the brightest objects in the observable universe. They are powered by supermassive black holes actively accreting material at very high rates, converting the gravitational potential energy of the infalling material into radiation with an efficiency far exceeding that of any nuclear process. A bright quasar can outshine the entire galaxy that hosts it by a factor of 100 or more, making the galaxy's stellar population invisible against the quasar's blazing light. Quasars are found predominantly at large distances, meaning they were more common in the early universe when more gas was available for black hole accretion. The most distant quasars known are at redshifts of 7 and above, meaning we see them as they existed less than 800 million years after the Big Bang, when the universe was a teenager by cosmic standards. The name quasar is a contraction of quasi-stellar radio source, because when they were first detected in the late 1950s and early 1960s, they appeared as point-like sources of radio emission that also emitted visible light, looking like stars in optical images, but with spectra showing enormous redshifts, implying distances far beyond any known star or ordinary galaxy. The redshift of a quasar named 3C273, the first quasar to be identified, revealed it to be at a distance of about 4 billion light-years, making it the most distant object known at the time in 1963. Its intrinsic luminosity was found to be about 4 trillion times the luminosity of the Sun, an almost incomprehensible level of energy output from a region smaller than the solar system. Starburst galaxies are a class of galaxies undergoing an exceptional rate of star formation, far higher than is typical for a galaxy of their size. The starburst is usually triggered by a gravitational interaction with another galaxy, which drives large quantities of gas toward the galaxy's center and compresses it, triggering the rapid formation of many new stars. M82, the Cigar Galaxy, is one of the most famous starburst galaxies, interacting gravitationally with its larger spiral neighbor M81. In infrared images, M82 shows a fierce wind of gas and hot plasma being driven out of its central starburst region, extending thousands of light-years above and below the galactic disk. A superwind powered by the combined energy of thousands of supernova explosions and the radiation pressure of millions of newly formed massive stars. Dwarf galaxies are the most numerous type of galaxy in the universe. They are small, typically containing between 1,000 and a few billion stars, far fewer than the hundreds of billions in large spiral galaxies. Dwarf galaxies come in several types: dwarf ellipticals, dwarf irregulars, and dwarf spheroidals. The Milky Way has dozens of known dwarf satellite galaxies orbiting around it. From the large and small Magellanic Clouds down to tiny spheroidal systems containing only a few thousand stars, some of which are so diffuse and faint that they were only discovered within the past 2 decades by deep sky surveys. Many more may await discovery in the outer halo of the Milky Way. Dwarf galaxies are important as the building blocks from which larger galaxies assembled, through a process of hierarchical merging that is a key prediction of the standard model of galaxy formation. In this model, the first galaxies to form in the early universe were small, and they gradually grew larger by merging with each other and accreting gas from the surrounding intergalactic medium. The large galaxies we see today, including the Milky Way, are the products of billions of years of merging of smaller progenitors. Let your breathing settle even more gently. In and out. The dwarf galaxies are drifting in wide orbits around the Milky Way. Some of them will eventually be absorbed, their stars added to the Milky Way's halo. Others will drift past and continue on their way. The galaxy is patient with this process. It has been accumulating smaller companions for 10 billion years and will continue for billions more. Galaxy clusters are the largest gravitationally bound structures in the universe. The Coma cluster, one of the nearest large clusters, contains over 1,000 galaxies in a region about 20 million light-years across, at a distance of about 330 million light-years from Earth. The mass of the Coma cluster is about 700 trillion solar masses, distributed among stars, hot intergalactic gas, and dark matter, with dark matter providing most of the total mass. It was the observation of galaxy velocities in the Coma cluster by Fritz Zwicky in 1933 that first suggested the existence of dark matter. The galaxies in the Coma cluster were moving far too fast for the visible matter alone to provide enough gravity to hold the cluster together. There had to be additional invisible mass. Zwicky called it dunkel materie, dark matter. Beyond galaxy clusters are galaxy superclusters, and beyond those, on the very largest scales, the cosmic web. The cosmic web is the large-scale structure of the universe, the arrangement of matter into a web of filaments, walls, and nodes separated by vast, nearly empty voids. Galaxies and galaxy clusters are concentrated along the filaments and at the nodes where filaments intersect. The voids between the filaments are regions of very low galaxy density, some of them hundreds of millions of light-years across. The Boat's void, one of the largest known voids, is about 330 million light-years in diameter. The cosmic web was first clearly mapped in the 1980s and 1990s as large-scale galaxy surveys began to reveal the three-dimensional distribution of galaxies across hundreds of millions of light-years. The CFA2 Great Wall and the Sloan Great Wall are examples of enormous large-scale structures, sheets of galaxies extending for hundreds of millions of light-years. The Hercules Corona Borealis Great Wall, discovered in 2013, is one of the largest structures known. a concentration of gamma-ray bursts spanning approximately 10 billion light-years. The James Webb Space Telescope has transformed our understanding of the earliest galaxies. In its first year of observations, JWST detected fully formed massive galaxies in the very early universe, at redshifts of 10 and above, when the universe was less than 500 million years old. These galaxies were far more massive and far more numerous than the standard model of galaxy formation predicted. Theoretical models of how quickly galaxies could form and grow in the early universe had to be reconsidered. JWST also imaged galaxies at lower redshifts in extraordinary detail, revealing previously unseen structures in their spiral arms, star-forming regions, and interactions with neighboring galaxies. One of JWST's first images released publicly was a gravitational lens field, SMACS 0723, showing a cluster of galaxies in the foreground that bends and magnifies the light of much more distant galaxies behind it, creating arcs and stretched images of background galaxies that would otherwise be too faint to detect. The image is the deepest infrared image of the universe ever taken, containing thousands of galaxies at a range of distances. The most distant of them, as they existed more than 13 billion years ago. It is a single image that contains within it billions of years of cosmic history, all visible at once, all accessible in the light that has traveled across the universe to fall on JWST's mirrors. The fate of galaxies in the far future of the universe is as various as their present states. The Milky Way and Andromeda will merge into a combined galaxy sometimes called Milkomeda, an elliptical galaxy lacking the orderly spiral arms of either progenitor. Other isolated galaxies will continue to evolve more slowly, their star formation gradually declining as they exhaust their gas supplies. Galaxy clusters will continue to grow as galaxies fall in from surrounding filaments. But on the very longest timescales, as the universe continues to expand under the influence of dark energy, the distances between galaxy clusters will grow ever larger. The local group will remain bound together. But the Virgo cluster, currently close enough to see with a small telescope, will recede beyond the cosmic horizon as dark energy drives the expansion of the universe faster than light can cross the growing distances. In the far future, an observer in the Milky Way or its successors will look out at a universe that appears to contain only their local group and the combined galaxy it will have become. All other galaxies will be too far away and receding too fast for their light to ever reach us again. The universe is becoming, very slowly, more isolated. Each bound structure, each local group or cluster, is an island of gravity that will survive, while the space between islands grows forever. The galaxies visible in the Hubble Ultra Deep Field, the 10,000 galaxies in a grain of sand patch of sky, most of them will eventually be beyond any communication with us. The light we see from them now is a record, already fading, of a time when the universe was younger and its parts were closer together. Let your body rest completely now, every part of you softening, the weight of your body pressing gently into whatever surface is beneath you, your breathing slow and quiet. The Milky Way is turning around you, its 100 billion stars and their planets moving in their orderly orbits. The Andromeda Galaxy is approaching, 2.5 million light-years away, silent, immense. The Virgo cluster is 65 million light-years away, M87 sleeping at its center with its 6.5 billion solar mass black hole. The Laniatea supercluster is flowing slowly toward the Great Attractor. The cosmic web stretches in every direction across billions of light years. Its filaments and voids arranged in a structure that grew from quantum fluctuations in the earliest instance of the universe. Quasars are blazing at the edges of the observable universe, their light billions of years old. Dwarf galaxies are drifting in wide, slow orbits around the great spirals. And somewhere, in the stillness between all of this, you are here, inside one of those spirals. In the early morning of the universe's long life, at rest. Before we drift fully into sleep, let the galaxies offer a little more of their extraordinary story. Dark matter halos are the invisible scaffolding around which galaxies are built. Every galaxy, from the largest elliptical to the smallest dwarf, is thought to be embedded in a much larger halo of dark matter that extends far beyond the visible stars and gas. In the Milky Way, the dark matter halo extends to perhaps 300,000 light years from the center. Far beyond the thin disk of stars and gas we see is the Milky Way itself. The dark matter makes up about 85% of the total matter in the halo, with only about 15% being the ordinary baryonic matter of stars, gas, and dust. The dark matter is not clumped in stars or clouds. It is distributed in a roughly spherical halo of individual particles, or perhaps some other form of matter entirely that interacts gravitationally but not electromagnetically. The evidence for dark matter in galaxies comes primarily from galaxy rotation curves. In the 1970s, the astronomer Vera Rubin and her collaborator Kent Ford made precise measurements of how fast stars orbit the center of spiral galaxies at various distances from the center. If the mass of the galaxy were concentrated in the visible stars near the center, as was assumed at the time, then stars far from the center should orbit more slowly, just as the outer planets in the solar system orbit the sun more slowly than the inner ones. But Rubin and Ford found that the rotation speed of stars in spiral galaxies stays roughly constant, or even slightly rises. At large distances from the center, far beyond where most of the visible stars are. This flat rotation curve implies that there is a large invisible mass distributed throughout a large halo around each galaxy, providing the additional gravity needed to keep the outer stars orbiting at their observed speeds. The dark matter halo was the explanation. Rubin's work, combined with other lines of evidence, established dark matter as one of the central mysteries of modern cosmology. Galactic halos also contain globular clusters, dense spherical groups of hundreds of thousands to millions of stars packed into a region only a few tens of light years across. Globular clusters are among the oldest objects in the universe, with ages typically between 10 and 13 billion years. The Milky Way has about 150 known globular clusters, distributed in a roughly spherical pattern around the galactic center in the halo. They are thought to be remnants of the early assembly of the galaxy, either formed in the early universe before the Milky Way's disk was established, or captured from dwarf galaxies that merged with the Milky Way in its early history. The globular cluster Omega Centauri, the largest and most massive globular cluster associated with the Milky Way, contains about 10 million stars in a region about 150 light years across. It is so massive and complex that it is thought by many astronomers to be not a true globular cluster, but the stripped core of a dwarf galaxy that was captured and absorbed by the Milky Way long ago, its outer stars stripped away by the Milky Way's tidal forces, but its dense core surviving as what we now call Omega Centauri. At the center of Omega Centauri, there may be an intermediate mass black hole, a class of black holes with masses between stellar black holes and the supermassive black holes at galactic centers, an object that would be an important missing link in our understanding of black hole formation. The discovery of galaxies as distinct extragalactic systems took a surprisingly long time. For centuries, the fuzzy patches of light known as nebulae were assumed to be clouds of gas and dust within our own galaxy. The philosopher Immanuel Kant proposed in 1755 that some of these nebulae might be island universes, collections of stars similar to the Milky Way but at vast distances, a prescient idea that would take nearly 170 years to be confirmed. William Herschel, the 18th century astronomer who discovered Uranus, compiled extensive catalogs of nebulae and recognized that some had the flattened disc-like appearance that his model of the Milky Way would predict for a galaxy seen at various inclinations. The question of whether the nebulae were part of the Milky Way or were independent galaxies was finally settled by Edwin Hubble in 1924 and 1925. Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory, the largest telescope in the world at the time, to resolve individual stars in the Andromeda Nebula and the Triangulum Nebula. Among the stars he resolved were Cepheid variable stars, whose distance can be determined from their pulsation period using a relationship discovered by Henrietta Swan Leavitt in 1912. Hubble's measurements showed that the Andromeda Nebula was nearly 1 million light-years away, far beyond the boundaries of the Milky Way as then understood. The nebulae were not gas clouds within our galaxy. They were galaxies in their own right, vast systems of stars at enormous distances. The universe was suddenly far larger than anyone had imagined. Hubble's discovery ranks among the most important in the history of astronomy. The stellar populations of galaxies reflect their history. Elliptical galaxies are composed predominantly of old, red stars. The remnants of star formation episodes that occurred billions of years ago and have since ceased. The lack of ongoing star formation gives elliptical galaxies their characteristic reddish color and smooth, featureless appearance. Spiral galaxies like the Milky Way have both old stars in their central bulges and halos and young blue stars in their spiral arms, where star formation is ongoing. The blue color of the spiral arms, visible in images of nearby spirals, is the combined light of many massive, hot, young stars, born within the last few million years from the gas-rich environment of the arms. The color of a galaxy, measured from detailed spectroscopy or broadband photometry, is one of the most informative properties astronomers can measure. A blue galaxy is forming stars, its spectrum dominated by the light of young massive stars. A red galaxy has ceased forming stars and is aging gracefully, its spectrum dominated by the cooler light of older stars. Galaxies of intermediate color, the green valley as astronomers call it, are transitioning from the blue cloud of star-forming galaxies to the red sequence of quiescent ones. Understanding what drives this transition, what shuts off star formation in a galaxy and turns it from blue to red, is one of the central questions of galaxy evolution research. The interstellar medium of the Milky Way is a complex, multi-phase environment. The diffuse hot gas occupies most of the volume of the disk, heated to millions of degrees by supernova explosions. The warm ionized medium is hydrogen gas, ionized by ultraviolet radiation from hot stars. The warm neutral medium and cool neutral medium are atomic hydrogen at lower temperatures. The coldest phase, the molecular clouds, is where star formation occurs. These phases are in a state of dynamic equilibrium, constantly exchanging material through heating and cooling processes, supernova shocks, stellar winds, and the effects of the galaxy's spiral structure. The spiral arms of the Milky Way are regions of enhanced density in the interstellar medium that trigger star formation as gas flows through them, maintaining the spiral pattern even though individual stars pass through the arms rather than being permanently attached to them. The molecular cloud Sagittarius B2 is one of the largest molecular clouds in the Milky Way, located near the galactic center. It is a region of intense star formation and extraordinarily complex chemistry. More than 70 different molecular species have been detected in Sagittarius B2, including ethanol, acetone, glycolaldehyde, which is a simple sugar, and aminoacetonitrol, a precursor to glycine, the simplest amino acid. The interstellar medium is not just hydrogen and helium. It is a laboratory of complex organic chemistry, and the molecules found in regions like Sagittarius B2 may be relevant to understanding the origin of the chemical building blocks of life on Earth and elsewhere. The Fermi bubbles are two enormous balloon-like structures of hot plasma extending about 25,000 light-years above and below the galactic plane of the Milky Way, centered on the galactic center. They were discovered in 2010 when the Fermi Gamma-Ray Space Telescope detected a bilobate structure of gamma-ray emission on either side of the galactic center that had no obvious counterpart in previous surveys. The bubbles are thought to be the remnant of a past episode of intense activity from Sagittarius A star, when the black hole was accreting material at a much higher rate than today and driving enormous outflows of gas from the galactic center. The edges of the bubbles are sharp, a shock front where the outflowing gas is ramming into the surrounding interstellar medium. The age of the bubbles, based on the dynamics of the shock, is estimated to be a few million years. Gravitational lensing is one of the most powerful tools in the study of galaxies and the large-scale structure of the universe. When a massive object, a galaxy or a galaxy cluster, lies between a distant light source and the observer, the gravitational field of the intervening mass bends the light rays from the source around it, acting as a gravitational lens. This can produce spectacular visual effects, multiple images of the background source, arcs of distorted light stretching around the lens, and in the special case of perfect alignment, complete rings of light called Einstein rings. The bending of light by gravity was one of the first observational confirmations of general relativity when measurements during the 1919 solar eclipse showed that starlight passing close to the sun was deflected by the predicted amount. Gravitational lensing by galaxy clusters is used to detect dark matter because the lensing strength depends on the total mass of the lens, including its dark matter component. It is also used to detect very distant, faint galaxies that would otherwise be too dim to observe, as the cluster lens magnifies them by factors of 10 to 100 or more. The Hubble Frontier Fields program and subsequent GS observations have used this natural telescope effect to image some of the most distant galaxies known, providing a window into the very early universe that would not be accessible without the amplifying power of the gravitational lens. The Magellanic Stream is a vast ribbon of hydrogen gas that arcs around about 300 degrees of the sky, trailing behind the large and small Magellanic Clouds in their orbit around the Milky Way. The stream is about 150,000 light-years long and was pulled out of the Magellanic Clouds by the tidal forces of the Milky Way's gravity over billions of years of interaction. It represents a significant reservoir of gas equivalent to hundreds of millions of solar masses of hydrogen that is slowly being drawn toward the Milky Way and may eventually fuel future star formation in our galaxy. The interaction between the Magellanic Clouds and the Milky Way, mediated through the Magellanic Stream and the gravitational forces at play, is one of the best studied examples of how the interaction between galaxies drives the exchange of material and shapes galactic evolution. Galactic winds are large-scale outflows of gas driven from galaxies by the combined energy of supernova explosions and the radiation pressure of massive stars. In starburst galaxies, where the rate of star formation, and thus the rate of supernova explosions, is very high, the galactic wind can carry substantial quantities of gas and metals out of the galaxy and into the intergalactic medium. This has important consequences for galaxy evolution. It can deplete the galaxy of the gas needed for future star formation, slowing or stopping the starburst. It also enriches the intergalactic medium with heavy elements synthesized in the stellar populations of the galaxy, contributing to the chemical evolution of the universe beyond individual galaxies. The intergalactic medium, the gas that fills the spaces between galaxies, is not a true vacuum. It contains a diffuse distribution of baryonic matter, mostly hydrogen and helium, at densities far below anything achievable in the best terrestrial vacuum chambers. This gas, called the warm, hot intergalactic medium or WIM, is thought to contain a significant fraction of all the ordinary matter in the universe spread through the filaments of the cosmic web. It is hot, heated by shock waves from the gravitational collapse that form the filaments, and difficult to detect because at these low densities it emits only faintly. Detecting and characterizing the intergalactic medium is one of the current frontiers of observational cosmology. The evolution of galaxies over cosmic time is one of the grand themes of modern astronomy. The universe at early times was populated by smaller, more irregular, more actively star-forming galaxies than the large, well-organized spirals and ellipticals that dominate the nearby universe. Over time, through merging and accretion, these smaller systems grew into larger ones. The intense star formation of the early universe has been gradually declining over the past 10 billion years as galaxies consume their gas supplies and the overall density of the universe decreases with expansion. We are living in a relatively quiet era of the universe's history in terms of galaxy evolution. After the peak of star formation activity that occurred when the universe was about 2 to 3 billion years old. The study of galaxy evolution is partly an exercise in galactic archaeology, reading the history of a galaxy from the properties of its present-day stellar populations. The stars in a galaxy carry the record of when they formed, from what material, and under what conditions. By measuring the ages and chemical compositions of stars in the Milky Way, astronomers can reconstruct the history of the galaxy's star formation, its merging history, and the chemical enrichment of its interstellar medium over cosmic time. The field of galactic archaeology uses this stellar fossil record to understand how our galaxy, and by extension other galaxies of similar type, came to be the way they are today. The galaxies of the universe are, in the deepest sense, the structures that make complex chemistry and life possible. They are the reservoirs of gas from which stars form, the recycling systems that process stellar material through supernovae and return it to the interstellar medium enriched with heavy elements, the gravitational structures that hold planetary systems together and keep them stable for billions of years. Without galaxies, there would be no stars. Without stars, there would be no heavy elements. Without heavy elements, there would be no rocky planets, no chemistry, no life. The galaxy is not a backdrop to life, it is a prerequisite for it. The galaxies do not need your attention. They have been turning for billions of years, and will continue for billions more. The great slow processes of the cosmos are running exactly as they always have, and in the middle of all that turning and drifting and glowing and colliding and merging, there is this quiet moment, this room, this breath. You are inside a galaxy, not beside it, not near it, but inside it, embedded in its disk of stars and gas, 26,000 light years from the center, in a relatively quiet region between two major spiral arms. The nearest star to your own sun, Proxima Centauri, is 4.24 light years away. The next nearest, Alpha Centauri A and B, are slightly farther. The stars of the Milky Way are sparse at this distance from the center, separated by light years of open space. The galaxy is mostly emptiness, just as the atoms that make up your body are mostly emptiness, just as the solar system is mostly emptiness. Structure built on space, organized by gravity, glowing with the light of nuclear fires. The galactic disk is rotating around you at this moment. The spiral arm pattern is drifting. New stars are forming in the molecular clouds of the spiral arms while you lie here. Old stars are dying in supernovae, sending their enriched material back into the interstellar medium. Red giant stars are shedding their outer layers in planetary nebulae, painting the galaxy in slow motion color. Neutron stars are spinning thousands of times per second in their tight, dense configurations. White dwarfs are cooling over billions of years in the galactic halo. In 26,000 light years toward the center of all this, Sagittarius A star is sitting quietly, a 4 million solar mass black hole surrounded by a cluster of young, massive stars whose orbits have been measured to extraordinary precision by decades of infrared observations, providing one of the most direct proofs of the existence of supermassive black holes. It does not need feeding tonight. It is patient. It has been there for perhaps as long as the Milky Way has existed, 10 billion years, and it will be there for far longer than any star currently forming in the galactic disk will live. The galaxies do not hurry. Their processes unfold on timescales that make human history invisible. The merger of two galaxies takes hundreds of millions of years. The formation of a star takes millions of years. The lifetime of a galaxy spans billions of years. We exist in an eye blink of galactic time. Our entire civilization, from the first cities to the present, is less than 1/10,000th of a galactic year. The galaxies are patient beyond comprehension, and they are beautiful. The great spirals, with their trailing arms of blue starlight and dark dust lanes, and the soft gold of older stars in their central bulges, the smooth ellipticals like vast golden clouds of ancient suns, the irregulars with their chaotic star forming regions blazing in blue and pink, the galaxy clusters with their hot intergalactic gas glowing in X-rays, and their gravitational lenses bending the light of distant quasars into arcs and rings. The cosmic web spreading across billions of light years, every node a galaxy or a cluster of galaxies, every filament a stream of gas and dark matter flowing toward the nodes, every void an almost unimaginable emptiness. You were part of this. Your body is made of atoms that were processed in stars that lived and died inside the Milky Way. The galaxy made you. You were looking out at other galaxies from inside your own, and tonight you were resting inside a galaxy, on a rocky planet orbiting a middle-aged star, breathing an oxygenated atmosphere built by billions of years of life, warm and still. Sleep now. The cosmos is large. The galaxies are many. And right now, in this particular corner of one particular galaxy, everything is still. Good night.